So good morning and welcome to the Finley Chair webinar. I'm Professor Hemant Jain. I hold the Finley Chair in the Gary Rollins College of Business at the University of Tennessee, Chattanooga. And again, it's really privileged to welcome you all to this webinar. This is the third in the series this year. We are going to have a couple of more excellent speakers. All of them have been very, very well received, very well attended. It's a webinar, at 50 plus people attending it. And we try to invite some of the top scholars in the AI data analytics area, especially with the applied focus to this webinar series. And we have been very lucky to have these things. But first of all, I'd like to thank Finley family, who has sponsored the chair, and which is what makes this webinar series possible. So many, many thanks to the Finley family, who has given a major donation to support the Finley chair here. So today it's my privilege to welcome Dr. Lee from Boston University. Dr. Lee is a Kelli Questrom Chair and Associate Professor of Information Systems at the Questrom School of Business at Boston University. He studies responsible application and the development and the impact of AI on e-commerce. And specifically, he is really an expert in mining and analyzing the textual data. He heads a center there called Business Insights Through Text Lab, BitLab. And as you know, text is becoming extremely important. 80 to 90% of the data which we have now available are all textual data. So it's very, very important to get and be able to analyze the information from the textual data. And it's a fairly, very, very challenging problem. And Dr. Lee is an expert in that area. Dr. Lee received his undergraduate degree from Columbia University in computer science. He got a master's from Yale and a Ph.D. from Wharton. So all Ivy educations, excellent background. He has published extensively. He's published in top journals in our field, management science, ISR. He got the best paper award in the ISR, and he got very, very prestigious Gordon D. Davis Young Scholar Award. So I think you can read more about him, things which he provided, but without taking too much more time, I will hand it over to Dr. Lee. You can share your screen, Dr. Lee, and start the webinar.
Thank you so much, Professor Hemant Jain. Let me share my screen. Hope you can see the screens.
Yes.
Okay. All right. So thank you so much, everyone, for coming. I would like to thank Professor Hemant Jain and Professor Shinjae Kim for organizing and inviting me to this awesome series, speaker series. I'm very honored to be here. Glad to be here. Thank you all for attending. Today, I would like to talk about this new paper. We're actively writing a draft on it. We call it InnoVAE, Generative AI for Understanding Patents and Innovation. This is a joint work with Zhao-Chi Cheng, who's my Ph.D. student, and Prasanna Sanitambe at UPenn. So successful application of AI has been, application of AI in creative tasks has been promising, right? So we've seen AI algorithms create music that are indistinguishable from human-made ones. AI has also been used to create not just a new drawing, it has been used to create new genre of paintings or art. It has been also used in hard sciences to produce novel molecules and design materials, right? We're not obviously fully automating these anytime soon, but AI for augmenting creative tasks and innovation is ripe for serious discussion. I think we are in the cusp of this. So as the data supports this, rising number of companies have been using AI for scientific discovery. Increasing research in science, top journals like PNAS and Science and Nature have been, in the last 2-3 years, have been coming out from material science, biochem, biology, in applying generative AI and other sorts of AI techniques. You can see some of these companies like Schrödinger, Atomwise, etc. They're all using AI, generative AI, and other forms of AI to actually advance hard science. These are some of the activities in this field, AI and drug discovery. Lots of activities in the last 3 years. So here comes the question of, can AI really innovate, right? There are a lot of these advancements, but can AI really innovate, or is it just a pastiche of a human ingenuity, right? So philosophy of creativity has a few things to say about this. First thing is, one school of thought says that creative agents need intention, and only humans can have intention at this point, so it should be left to humans, and just forget about it. Computational creativity should be abandoned. There are people who think this way. However, there are creativity literature that says, no, we should start somewhere, and let's create some framework and algorithms to do this. And one of the first axiom that they have is that before creative agents can actually create creative artifact, it needs to first recognize creative artifacts, right? But before AI can, whether it's AI or humans, right? It needs to first recognize before creating. Now, before AI or human can recognize innovation or create a creative artifact, it should be able to represent innovation, right? So our research question is simple. Can AI represent innovation? And how helpful is this representation? That's what we're trying to do here. We prototype what we call InnoVAE. VAE comes from the fact that we're using variational autoencoder to estimate the disentangle representation of patterns using both structured and unstructured data. So disentangle representation is we first do this via generative AI. And representation learning just means that it maps real-world object into a lower dimensional vector space with the certain properties sustained. This disentangling part here is additional sort of a constraint that says each dimensions. So representation learning in the end, simply put, embeds any objects, whether it's say text, like word2vec or any sort of object into a lower representation, a low dimensional vector space. It's a feature engineering, so to speak, right? And this entangling part is additional sort of requirement here that says that each dimensions in this lower dimensional vector is extracted in such a way that each axis are statistically more independent. Therefore, it's more semantically orthogonal. What this means is that the movements within the space are rendered meaningful and understandable that you wouldn't otherwise get. So here's an example of disentangle representation learning. If you take all the rectangles in the world and give it to a successful disentangle representation learning algorithm, you should be able to figure out that you can actually represent any rectangles in just two-dimensional space, right? You can have a length and width, right? Or hypotenuse or length, hypotenuse or width, right? So with this, it can represent any rectangle and generate any rectangle. And disentangle representation learning should, by looking at all the rectangles, come up with these two dimensions. That's the idea of disentangle representation learning. So now, ideally, if we apply this in a multimodal object of patent, we can probably extract out interpretable factors of innovation that comprise this set of patents, whether whatever patent group we use. And patents should now reside in an interpretable vector space that characterize patents by their factors of innovation. That's our goal here. And specifically, for example, if we use computing patents, they may reside in dimensions like security, human-computer interaction, or other things that might be talked about in the patent document. So the resultant contribution overviews are as follows. We build this space, what we call innovation space. Oh, by the way, do you hear like construction noise? Is it too loud?
No, no.
No, we are good right now.
Okay, great. All right. All right. Sorry about that. All right, so our first contribution is what we call innovation space. This is the vector space that the algorithm embeds all the patents into. So it facilitates exploration into patents, innovation, and firms. And as I'll show you in this presentation, there are many applications. We sort of built a ladder, and this introduces, in effect, lots of low-hanging fruits. We can, as a first example or application of this innovation space, we rank exceptionality of patents using some geometric operationalization of philosophy of creativity within the innovation space. We also do some firm-level engineering within this innovation space. You can represent firms within this innovation space by finding a centroid of all the patents that's owned by the particular focal firm. Right? And then we can also characterize and engineer a variable based on this innovation space. So as I'll show you, some of these engineer variables are very good at predicting. It has lots of signal for predicting things like Tobin's Q, as much as like cumulative number of patents or for citations for predicting Tobin's Q. And this is this is a very preliminary empirical prototype of deep neural network as an invention of method of invention, as talked about by Ian Cockburn and others. So here's a visualization of innovation space. So you can see here, I'm just visualizing three-dimensional. Factors are sort of encouraged to be independent and interpretable. I'll talk about how. So each of these points would be a patent. The key point here are that factors are distinct and data-driven. Directions are rendered meaningful, meaning that this patent B here, in comparison to patent A, is a increased factor of 2 and 3, whatever that may be. This is not possible with other visualization algorithm and methods, such as PCA, which does exactly the opposite, Tisney or traditional autoencoder, because these lack interpretability and orthogonality constraint built into the algorithm. So you can also, this is obviously a wrong sort of representation. Firms are not just the addition of all the patents that they own, but you can still represent each firm by finding a centroid of all the patents in this space. So what does this do? Why do we care, right? So good disentangle representation enables the following: control generation. So with this trained model, we can now generate new patents. Second, this is more interesting part, is that we can now, within this innovation space, geometric interpretation, comparison, and visualization is now possible at the patent level. I'll show you an example of doing this, where we identify creativity level of patents purely from the data. Innovation factor level, we can extract factors of innovation that comprise particular set of patent groups. So if you apply this in a different set of patent groups, different set of factors will arise. You can also then do lots of firm level comparison and visualization and characterization. And you can situate firms in the innovation space for comparison. Here are some more specific questions you can ask. We can ask and explore, what can you get if you combine patent A and B? You can automate combinational creativity. How exceptional, you can ask how exceptional or unusual is a patent. It's not necessarily better, but it's always compared to the average of the group. How exceptional is a patent, for example, iPod related, with respect to specific technological factor like user interface, which is automatically generated or estimated. You can also ask what innovation factors increase or decrease over time. You can do this, we can estimate this every year, and we can see particular factors or axes rising or dying down, right? what company excels in technological factor X, right? We found firm A, what innovation do I need to boost up to be more like firm B? Right? So we can do all of these. And let me now just briefly go over our application or our empirical method. Why generative models are needed? First, this is we apply generative model. So as opposed to discriminative model, which models a probability of label, if label is given X variables, generative model just models data generating process, probability of X, or joint probability P, X, and Y if the labels are given. So now take it back to the patent task. Let's say we want to sort of rank patent on their creativity or innovativeness. This is almost infeasible. Why? Because it requires vast amounts of knowledge, right? You need to have the patent examiners be experts in that particular field. There's so many different fields. Someone who can work in a particular group of patent cannot work in a different group because they're totally different. It also needs to be updated. It's very intensive, labor intensive if humans were to do this, right? To come up with the label. There's also no existing Y or the label on creativity. Right? It needs some sort of data-driven approach to dissect patents. This is why we use this disentangled generative model and to decompose patents into independent and interpretable factors. Now, there are some, disentangled representation learning is still a rising field. It's a nascent field. There are a lot of problems, and we're not saying this is the right model, right? But in the end, what we can show is that these prototype and the estimation that we do with this model can be very helpful. All right, so here's a bit of background on our model. We situate patents. The end goal is to situate patent in an innovation space with this variational autoencoder. Variational autoencoder, the plain vanilla variational autoencoder, all it does is it can take any sort of object, multimodal object, in our case, patent data, and the encoder basically finds a latent, just a lower dimensional representation of this object. And the decoder then takes that and then tries to replicate or recreate or reconstruct that object, in this case, again, patent. You can do this with, say, jobs, customers, companies, anything, images, right? So we make a data generating assumption here that humanity or the inventor samples a random latent factor, and we call that innovation embedding. And then humanity then implements the concept vector into real world instance X patent. And we're just trying to estimate this process. On top of that, we customize loss functions such that this disentangling is internalized. First of all, one of the most important things is reconstruction loss, where it sort of enforces this representation to be good, such that we can reconstruct realistic patent or any object. Right here is a supervision loss, so we can also, this is an inductive bias to sort of ensure that we keep a realistic object to be created, and the representation is pushed in a way that it's more realistic. It also adds more constraint. It's as if in a rectangle, you're saying, here's all the length, just find the other dimension, right? So it's making it easy for the algorithm to estimate this dimension. It's sort of your restricting degree of freedom. The middle part here is the disentangle inducing term. So we assume that the prior of this distribution, latent variable, is distributed according to isotropic Gaussian, multivariate isotropic Gaussian. This is what sort of pushes the dimensions to be more orthogonal. So think of this is a semi-supervised multimodal beta VAE. It's a beta VAE is what we started with. As a sort of nonlinear factor analysis or dimension reduction algorithm with lots of benefits that weren't possible before. So for example, first of all, this is multimodal, can incorporate structured and unstructured data natively together. Power of neural network performance and framework it comes as an added benefit. It's easier to add constraint through architecture or customized loss function. Third, we can do control generation of any multimodal entity. As you may have seen, lots of these things are now close to being realistic and human generated. We can also easily add the supervision with any known key variable. For example, in the patent literature, the number of claims have been studied to be really important. Things like that could be enforced. We can also internalize the centennial representation, which comes with the added benefit of interpretability. So it was that prior assumption. We now go to, we apply this in the US patent filed under G06 category. It's patents on computing systems. So this is about 240 patents between 1980 to 2010. It includes things like PageRank by Google, multi-point touch system by Apple, you can swipe by 3 fingers and things like that. And just for this prototype's sake, we wanted to keep it economical. We used the patent abstract as for the textual data. And for structured data, we use these: word count of the abstract, number of patent claims, backward patent citation, backward non-patent citation like scientific citation, bibliometric originality measure that's been used a lot. And with this, we did a bunch of model validity tests, which I'm going to skip because lots of it is boring. We do show that latent vector signal strength for downstream prediction task is much greater than, say, other representation algorithms. We also have a validation of innovation space using AMT, Amazon Mechanical Turkers, and patent reconstruction. This is what I'll show you. So here's an example of a particular patent. This is the original text. This is the multi-point touch system, a computer implement method for using conjunction with the compute device with the touchscreen display comprise, and so on. And this is the generated one. Of course, you can see the grammar is all broken, but you can see the green highlighted text is repeated, it's recovered, right? And we also did some sort of a fidelity metric. Of course, this is not usually used in this context, but token similarity measured by Rouge 1 score. This is used in machine translation, and the state-of-art summary model achieves about 40. We achieved about 31.4. This is basically figuring out, in this case, unigram similarities, co-occurrence. Sentence complexity, we also calculated a bunch of readability score. It was pretty similar, but these things are more internal validity. So here are some, again, innovation factors that were estimated, purely data-driven, extracted with constraint to guide the algorithm. These things, okay, you can see that some of the dimensions are useless, or it's controlling for things like punctuation, the way the writings are written. But there are axes that arise automatically, things like human-computer interaction as described by a set of these words, like interface, control, mouse, texture, color, polygon, body, reflection, render, virtual. You can see there is broadcast, ergonomics, information retrieval, hardware, automation and control, finance and transaction, payment, money transfer order, recipient, sender, merchant, payer, payee, request, security pops up. Remember that this is computing patents, right? And if you were to apply this to some other subgroup, you will come up with a completely different set of axes of innovation. So first fun thing we can do is patent fusion. So within this latent space or innovation space, we can simply add or take an average, or you can take a median or anything and do a combinational creativity here. So simply we can add latent embeddings of patent to get a new one. And then we put that embedding into decoder and tell it to generate me a new patent, right? And we can do this. And in this case, here are some examples. I'm not going to go into all of these, but here are some fun ones. So we took a patent that's about using multiple search engines to search multimedia data. And then another one, so we took one from IT and one from finance. This patent is about system and methods for rapid updating of credit information. And when you combine it and tell the algorithm to generate, you get very close to this existing patent that's about process for protection against fraudulent use of smart cards and device for use of the process. Right? So like search engine plus the card updating, fraud detection. Right? This is an example. You can do this and then generate as many as you can. I'm going to skip this, but this is like the first application that we have used of the innovation space. We wanted to explore into innovation space, the innovation factors themselves, patents, and firms. First thing is patent level exploration. In this application, we wanted to rank overall creativity of patents, purely data-driven. And to do so, we use a guiding theory by Margaret Bowden. She has a bunch of seminal work related to creativity. And she has this framework of how you think about a creativity. And Jared Wiggins actually formalized this. And she talks about what she calls a conceptual space. It's a space for humans. It's a structured way of thoughts and frameworks and rules and constraints. Right? So this is a way of thinking about an object or creating something, whatever that is. And for machines, as Gerald Wiggins formalized, it's an algorithmically defined representation space, easily understood, something like an embedding space. He doesn't really say it's an embedding space, but we can think about it. It would be an example. Right? So this conceptual space defines rules and frameworks and constraints on how you would come up with a particular set of creative artifacts. Think of a game of Go or Sonnet. It has rules, right? So, and we always follow that rule to play a game of Go or create a sonnet. And then given this conceptual space, Margaret Bowden and Gerald Wiggins define three different types of creativity. First one is the obvious one, the combinational one. It's the basic level. It's obvious combination of extant ideas within a conceptual space. So in this case, you take existing objects or existing instantiation of whatever, sonnet, for example, and you combine it. So if you copy paste particular parts of sonnet and still form a valid sonnet, that would be a combinational creativity. So any sort of startup ideas has been pitched as, say, like Uber of this, Airbnb of that, or Tesla of this, or Google of that. That would be a combinational creativity, right? Then the next level up is exploratory. Exploratory creativity is basically within this conceptual space that you instantiate a point there, or you create something that was never there before, but you knew that it was possible, right? So this is not just achieved by combining a simple, combining two or three different objects, because you could have a point that lies outside their convex hull, within a conceptual space. Lastly, the highest form or the most unexpected form of creativity is the transformational one, or transformative creativity. And this goes beyond the boundary of conceptual space. It's as if you were to represent this conceptual space as some sort of a space, it'll be you come out with a dimension that's orthogonal to every existing dimension, right? That will be a transformational. So Picasso, Cubism might be called transformational, things like that. So again, let's say if we take a sonnet example, combinational one might be you take an existing sonnet, copy paste, and then create another sonnet. Exploratory, you just write a new sonnet of your own from the scratch. Transformational is, well, I don't care about sonnets anymore. I'll come up with my own form of poetry and call it Sonnet 2.0. That will be transformative. Okay. So these are three levels of creativity, and we operationalize this within this innovation space. First thing is we define So this is a representation. Again, this is just two-dimensional for visualization's sake. We first identify or define what we call innovation frontier. This is simply the convex hull of existing patents. That's what we will call innovation frontier. Second is we then take the minimal bounding box of the existing patents, and we're going to call the conceptual boundary. Right? So here, after we define these two frontiers, what we can do is the following. The gray ones are, say, the ones that was generated or patents that existed up until, say, year 2019. And in 2020, let's say a new patent gets created. And these are their placement within this innovation space. You can see the orange one may lie within the innovation frontier or the convex hull of the existing patents. We're going to call that the combinational. By definition, you're just taking existing things and then you're coming up with a new one by taking some linear combination of existing patents, right? So within a convex hull, anything that gets instantiated within the convex hull, we'll call that combinational. Anything that gets instantiated outside of the convex hull, however, within this conceptual boundary, which means that we knew how to instantiate, or we knew that it could exist and instantiate it, that will be exploratory. And anything that just sits outside of this minimal bounding box or the conceptual boundary, we're going to call that a transformative. You can think about green dots actually just like rising out of, like sticking out of your screen. That would be also a transformative, right? But I couldn't visualize that. So then we did some descriptive comparison of these different types of innovation. So we see that the vast majority are combinational. Of course, remember that we have to estimate this every year, right? Therefore, what was once transformative could later become combinational, right, by the definition. This is accounting for that too, the yearly difference. Overall, majority of the patents or innovations are combinational. Some are exploratory. Very small set of patents are transformational, that it gives a rise to new factors of innovation. Combinational, we also see that combinational innovation experience stable exponential growth, while this exploratory and transformative ones stay about the same, remain steady. So here is just some comparison. Creative ideas get relatively more scarce. In 1980s, every 3.6 combinational come with one exploratory and transformative. By 2010, that number, for every one exploratory and transformative, you get about 200. In fact, this thing is very reminiscent of this recent paper by Stanford folks, why ideas are getting hard to find. And I'll talk about that later within the context of Econ of AI. We also compare the 10-year forward citation. So this is a measure used in the patent literature. Of course, this is a future data. This is why we stopped at 2010. We wanted to compare, calculate 10-year forward citation for everything. 10-year forward citation just measures within the 10 years until after it was issued or published, how many other patents cite that patent. And it's a good proxy. It's most widely used proxy for scientific impact. Of course, this is not a good measure because it's a future one. You can't come up with the 10-year forward citation. It's a good measure ex ante, post hoc. So we compare this too. An average number of received forward citation varies statistically significantly. You can see that for this one, combinational, exploratory, and transformative, you see that in decile, many of the transformative and exploratory ones belong in the top ones, top deciles, which means, within 10-year frame period, exploratory and transformative ones do get cited more. And this is just a graph of by the year, combinational versus impossibilistic, which is addition of exploratory and transformative. What we did was we also describe their market value. So there is this value called Kogan value, which uses a short-term market reaction to put a dollar value to a patent. So we just, again, calculated and compared. You can see that while the force citation was higher, 10-year force citation was higher for those exploratory and transformative, combinational innovations show higher market reaction. Of course, this might be due to the fact that Kogan value uses short-term market reaction. This could mean a lot of different things. That the value could be not perfect, or that combinational innovations are the ones that market knows how to monetize in the early years. Maybe this will change, but this is interesting to see. Now we go to the firm level exploration using innovation space. We define simply what we call innovation index. So given patent X, innovation index I will be an absolute difference between posterior mean and prior mean at dimension I. Remember, dimension I is a technological factor. So this means that if you get high index, the patent is exceptional in this technological factor, meaning it's unlike most patent in that group. I see a chat. Okay. All right, it was, okay. All right, so low index means that the patent is more average in this factor, right? So what we did here is we then ranked companies within particular innovation factor. Again, these innovation factors are driven by the data, and it's extracted from the data. We didn't tell it to say, give me human-computer interaction. It just estimated that by itself. And here is a bunch of firms, and then innovation index within this particular technological factor. So take human-computer interaction, for example, and you can see within this 1980 to 2010, Nintendo comes up, is the top and most innovative in human-computer interaction, followed by Pixar and immersion. For automation, Intertrust, followed by Silicon Motion, and Toyota wins out. These are the top three. For finance and transaction, Visa, CME, and Salesforce win out. They come up top. For connectivity, this was unexpected, but I figured out why. But Wells Fargo comes out on top for connectivity. What happens is Wells Fargo has lots of patents related to document transfer. If you see lots of, they do lots of mortgage, and they have a lot of patents on that. Followed by Westcorp, Commvault, for document processing, Fuji, NTT, and Dell. So you can see that take any given set of patent groups, and then you can rank, and then you can tell the VAE to generate factors of innovation, and then rank companies in these factors. This is just another example. Here's some visualization, which is pretty standard because you can do this with all kinds of different visualization and dimension reduction algorithm. However, one key difference here is that the directions are meaningful here, right? So let's say you are to do this in Disney. You don't know what the directions represent. Let's say you do this with PCA. Each dimensions are some jumbled up version of distinct factors. You don't know how to interpret that, right? This one, it's pushed to be more singular and meaningful in each direction. This is another one.
Dr. Lee, I have a quick clarification question for you.
Yeah.
So how do you come up with these technological factors or these dimensions?
Oh, so
how many dimensions and which patterns?
Yeah, that's a great question. So how many dimensions to come up with would be a hyperparameter. We decided we would tell it to come up with n number of dimensions.
Okay.
And that we can, yeah, go ahead.
No, so you just give it an n number, deciding how many dimensions you want, right?
Yeah, and you can decide that partly by the data fit. You can tell it, what you can do is you can start with like large numbers, and what would happen if it's constrained well, and then there's enough data set or data, a lot of factors will be, jumbled up garbage nonsense, and then things that are meaningful would get estimated. Now, this is why you would have to add lots of inductive bias, like supervision with known variable to reduce the degree of freedom. Otherwise, the algorithm would have a problem. In fact, there is a ICML paper that says you can't really do a totally unsupervised entangled representation learning. So this is why if you add inductive bias as much as possible, or domain knowledge or constraint, it'll do better.
Okay.
Great question. So here is now downstream application. This is where you can sort of see whatever I just did before kind of makes sense. It's cool, it's fun, but you can always ask, so what? Like, how do you know for sure? I mean, besides the AMT human tagged internal validity test, a lot of these are you can't some suspicious or audience might say, yeah, well, that's cool and all, but how do we know? How do we validate it, right? So here is one example of downstream validation. So we use innovation space to predict something that's meaningful. Of course, it's not causal. Nothing here is causal, but here's one example. So what we did here is we used innovation space and engineered variable at the firm level. Remember that in this space, we can represent firm by a centroid of all the patents owned by that firm. And we can actually calculate a bunch of different things, geometric representation. We did 3, for example, here. First thing might be average square distance. Let's say this is a firm and these are all patents owned by this firm. You can calculate average square distance as you would do in clustering algorithms. This will be higher, so they're spread apart more, and lower means they're more compact. They're within this particular local region of space. We call that average square distance. This is similar to what the patent literature talks about, technological diversity of a firm or knowledge stock, right? So there are papers that sort of, this measure is mimicking technological diversification and coherence. We also engineer a bounding box. So this is a big one, it's lower bounding box volume. This relates to potential of technological synergy within an organization, where you can do lots of combination with the existing patents here. This is reminiscent of technological synergy. Then there's an average saturation. So take any given patent owned by that firm, you can see how saturated that local region is, which sort of measures how crowded is a particular patent. It's related to patent thicket idea or patent fencing idea. You can see lots of companies might create a patent thicket such that other firms cannot enter and do things in that area. Oops. So this is average saturation relates to patent thicket. So you can do more, but these are 3 things that we decided to calculate. And here's what we did. So Tobin's Q, used in lots of literature, is basically total market value of firm divided by total asset value of the firm. And we're trying to predict this with a bunch of things that were already used in the literature, plus our engineered variable. In order to extract as much signal as possible, we ran a linear model too. I'm not showing it here. The traditional linear model as done by the literature shows the same result. But we then put it into XGBoost to extract out all the interactions and then linearities. And then we fitted it with the SHAP, right? So SHAP is a interpretable machine learning algorithm that basically figures out the attribution or the signal strength of a particular value for predicting Y variable, accounting for all the nonlinearities and interactions, right? So again, we fit all of these X variables, put it into XGBoost, and then we apply SHAP to get the feature importance of a particular variable. This is different from coefficients. This SHAP is the only way. It comes from the Shapley value, And it's one of the only ways to actually attribute feature importance with the particular theoretical implications. So you can see again, total square distance, average crowdedness, or these things come in here. So you can see again here, cumulative patent count is the most important. I mean, we knew that, the literature knows that, and it does come out at top. How many patent the firm owns is very predictive of the Tobin's Q. However, average crowdedness comes up second, important. That was our variable, right? This is what we engineered in the innovation space. The next one is cumulative for citation, right? Cumulative for citation is again known in the literature to be very important. This is about, it's basically how much how many times the patent owned by a particular firm, say Google, gets cited in the future, right? So it's pretty predictive. Then our other variables, engineer variables, come after. Cumulative claims, no, this is not our variable. That's again, it's a very well-known important variable, but average square distance is our variable, right? So you can see that average crowdedness or the density of nearby patents related to patent thicket is pretty important. And this is our variable that even beats things like cumulative claims count, which has been known in the literature to be very important for Tobin's Q and things like that. You can see there are other sector things coming in. They're about the same. Different sector are important. And now again, what we can do here is we can collect all patents owned by firm and obtain the average patent latent embedding. So here are just like fun things that we can do. What I've just shown you is some downstream task validation. This is just another fun thing that we can do with this InnoVAE. We collect all the patents owned by a particular focal firm and then take the centroid, then use the InnoVAE decoder to produce a new patent. What this means is that it averages out all the patent owned by this firm and comes up with some sort of representative patent of the firm. Here are some examples. Again, this is generated by the, and so it has lots of broken grammar. You can train it to have a good grammar, but that's just a waste of time. Here's an example for Apple. A method for provide a user interface for a computer system, have a plurality of a computer system, each of which be capable of computer system. So it's like what Apple does. Device be connected to the display device via communication link. Let's see, say Ford, a method for control the operation of a motor vehicle, right? So that's what Ford does, right? Perhaps things will change when they venture into EVs. Adobe, a method for controlling the operation of a printer, such as a printer includes steps of receive a print command. So it is about printing and things like that. You can see also Google, Samsung is more like portable computer, have a housing and a display screen. Google, a system for transfer fund between a sender and a recipient, includes a sender and a receiver. I guess this is a bunch of, they combine a bunch of things. Microsoft, a portable computer system, have a screen and a keyboard for use with a computer system. So I guess like PC. The main body have a display portion and a display portion. Okay, that's recursive. Here's again what we can do. We can find top 3 nearest patents given the firm, and it's sort of representative of the firm. Right? Apple, portable electronic device with the interface reconfiguration mode, user interface widget for selecting a point or a range, user interface for providing consolidation and access. And I'm not going to go through all of this. Let's go forward. System and method for designing automotive structure using adhesives. System and method of virtual flow bench simulation. Method for determining addendum and binder surfaces of spring-back compensated stamping. That I have no idea what that means. All right, so I want to take a step back and situate this work within the context of econ of AI. So,
Lee, can I ask you just another quick clarification question? So
Sure.
in your previous screen, you used data from which years here?
Oh, this is basically, let's see. But this is at the, like, we took the last model and then we just found this.
Because it's kind of interesting. So for Microsoft, nothing related to software showed up there.
Mm-hmm. Yeah, so I
Like,
guess,
like operating system or software or Windows or anything.
yeah.
So I don't know, it's related to the year you picked up the data from, because their software patterns might be older.
Yeah. So perhaps remember this is, we took the centroid. So centroid is always moving, and so it's probably moved away from the software and PC stuff.
Okay.
Good point. So as this is why I think this is another point why a data-driven way is the way to go, because our knowledge it doesn't update as fast as the number of patent that comes out per year. It's just vast majority. It's so many patents come out. So even the patent examiners, when you read some of their interviews, they have a hard time like keeping up a lot of times in the field that are just like exploding. The computers don't have a problem with that. Of course, this method has lots of different problems, but it can probably be improved over time. So contextualizing our work within the framework or the literature of econ of AI and innovation literature, there's this fascinating paper by Stanford folks, Bloom et al. It's titled "Ideas Are Getting Harder to Find." And what they found is, after examining lots of different industries and firms and whatnot, they found that ideas are getting harder to find, which means the transformative exploratory ideas, the numbers are decreasing, or our sort of creativity, productivity is decreasing, but we are still, innovation, like technological innovation is still increasing. How is that happening? Actually, we're just putting more people into it. So one of the figure given there is the Moore's law, the famous doubling of conductor, speed and things like that. Compared to 1970s, right now, I think they had to put like 19 times or 20 times more human to produce that effect. So it's getting harder and harder to do well or be creative. And this is attributed to a bunch of different effects, like what Cohen has talked about, low-hanging fruit effect. All the low-hanging fruits are plucked. There's also burden of knowledge, as talked about by Jones. What does this mean? So you can stand on the shoulders of giant, but it's hard to climb up to the shoulders of giant, right? So there's also curse of dimensionality. Lots of knowledge. You can see that there are a lot of different knowledge in the world, and they are sparse graph. And to connect and come up with this innovative creative artifact is just getting harder and harder. You need to learn way more than before. So all of these combined show and sort of explain why ideas are getting harder to find. And thankfully, in 2019-20, a bunch of econ of AI folks have actually wrote about this. They posit that deep learning as a general purpose technology and invention of method invention can perhaps, they conjectured, improve performance in existing search-intensive research projects, right? And other people have said, and find useful combination in complex discovery space. InnoVAE have just, we have prototyped and showed you could do this within the patent setting, right? So this is a bit of fun things. So in 2019, someone filed a patent to automatically draft patent, given human provided claims. So humans can provide the claims. That's the key part of the what distinguishes this patent as new, right, and exceptional. Given that humans can provide this patent actually is an algorithm to generate and draft the entire patent. Sorry, now you're hearing the, all right.
Now we are hearing a lot of noise, yeah.
Okay, they have started working. Okay, this should be better.
Yeah, much better,
Okay.
much better.
Okay, yes.
So I have another question before, I think in your previous slide.
Mm-hmm.
So the another point of view of not having as much transformative innovations has been that there is less and less focus on the basic research over the last 20 or 30 years than it was before. And so there is actually a lot more focus on the applied research. So some of the basic research which used to be done by Bell Labs and DODs, and a lot of those have disappeared. Even like an IBM and all these companies are focusing a lot more on the applied research than the basic research. What's your thought on that?
I haven't looked too much into the data on that. I don't know if that's actually going on or not. I am not sure. But these folks have said that the efforts are increasing many folds. It's just that our this is very reminiscent of the let's see, it's this figure that we found, right? So this is saying that the combinational ones are exponentially increasing, but the ones that are actually creative are not. Going back to your question, I have no idea. I mean, I don't know if they're actually increasing. How do you define, what did you call basic science?
Basic research, basically. So like there used to be 30, 40, 50 years ago, there were a number of organizations or corporations where they would pretty much basically take you, put the scientists in, and let them do whatever they want to do. Okay, even there was culture in Bell Labs, which was owned by AT&T, that people could do pretty much what they want to do, whether it's related to their business or not. And that is what created a lot of transformative research, like transistor descriptor. Transistor was done by the Bell Labs and other things. So that's kind of idea is that those organizations are less and less now because the corporations are under the pressure to produce profits, and so the basic research or the fundamental research investment is a lot lower.
Yeah, I mean, I do think that might be, I don't know. I don't know how true that might be. It could be a bunch of these effect, right? I mean, the focus might be still there. It's just maybe actually just getting harder and harder to find this next groundbreaking things. I mean, I guess if you could look into, say things like NSF grants and numbers and, number of people, the researchers who are considered doing the basic science, the foundational science, you can see that perhaps it's been increasing, but it's, I think, all of these impact giving a rise to, we're just the transformative ideas are getting harder to find. Maybe that's why we're feeling this, right? And yeah, I mean, so general purpose technology or a method of invention could, lots of this combinational creativity could be automated. It has been conjectured, and we have shown an example of that. However, to come up with like, how do you do transformative ones? That's still unclear, right? Like, yeah. Yes, Jin?
Thank you. Thanks, Kay. So my question is like, so when you started the data set, you were focusing on the computing, the G06.
Yep.
Yeah. So my question is like, if you broaden your data set to other patents, and then I think maybe, so within the computing world, it's getting saturated. So maybe we cannot really see much new things, but now we like hearing like quantum computing coming up. So maybe with the physics and computing, so maybe if you can like broaden your data set, maybe that we can have some interesting findings. Just a suggestion. Thank you.
Yeah. No, I think this is precisely where what this is getting at, right? So these folks have said, improve performance in existing search intensive and find usable combination in complex discovery space. Think of complex discovery space as this innovation space. And if you add like physics, as you mentioned, and computing, perhaps you can sort of see these quantum computing things arise, and then maybe like a new innovation factor, if there are enough of it getting patented, it'll randomly pop up. In a certain year, it'll pop up. I think this is also another, you bring up a good point. What you can do is, well, computing CS expert, it's hard for them to be an expert in physics, right? So what you can do is you can probably train the algorithms to just combine different fields and then come up with the combinational ideas and then let the humans sift through it. It's not going to be able to automate, here's a great idea, look at it. It's going to be more like, here are a set of what might be a good idea, and you confirm it, right? So you could do this, and this is what they mean by useful combinations and improve performance in a search-intensive research project. We're trying to take the power of AI to try to alleviate curse of dimensionality, alleviate burden of knowledge, and actually build a ladder so that other things are lower hanging fruits. So this one was pretty fun because one thing that's a bit meta is that we were able to actually generate this using patents that comes up until 2010. And this is within the combinational hall of existing things up until 2010. It was just a matter of time. Having said that, generative models that I'm presented today still needs a lot of work. The set of these algorithms. A lot of things prevent one from estimating this, like posterior collapse. Unsupervised disentangling is not possible. That was a 2019 or 18 ICML Best Paper Award. Training issues, it's just hard to train these models. Sometimes unrealistic instances pop up, and a lot of garbage might pop up. That's a real issue. But again, the current algorithm, as we have shown, as a prototype, should be able to provide a subset of useful concept of non-existing patent claims for humans to filter through. And then you put into this, then you get a full patent now. So I want to conclude here. Takeaway is that generative AI can reveal insights about patents innovation by situating them in an interpretable innovation of innovation factors. This approach enables lots of different things like interpretation, comparison, visualization, and augmented creation. Can be applied to anything, literally. So I've been talking to my colleagues like Dan Rogg and other folks doing this. Can you please apply this to, like, say, job skill space? Think about jobs, right? And the description of jobs. Now these reside in a vector space where each axis are skills, perhaps. You can do this with the products and embed in a feature space. You can do this with the company. And there are a lot of other new possibilities brought forth by generative approaches in business. I think we should all explore this. Instead of just using discriminative prediction model, we should approach some application with the generative approaches. And that is the end of the talk. Thank you.
So we're open for questions. Questions for Dr. Lee. Yeah, Dr. Zhang, I think you had a question.
Okay.
Any questions? No? Yeah, please.
Joan, we cannot hear
you're on
you.
mute. We can't hear you.
We can't hear you.
Sorry, we can't.
Can you type your question through chat? Maybe ask your question through chat.
Perhaps your speaker input has been changed. Sometimes do that. Oh, there we go.
Now it's better.
So one just curiosity is, I think, because it's so applicable, DK can run the algorithm on the paper of certain area, maybe IS, and then factor it out, and similarly can come up with a new, say, research ranking for the department, school, and individual to see that who's more creative or more concentrated on the one topic or venture out. I think that's one.
Yeah.
just to have fun. And but for more applicable idea could be, you could actually find a new research topic, right? Just by parsing all the previous, say, paper, and this is an unexplored area, and then although it's all the like Oracle, like you cannot interpret as it is, but with expert knowledge, with understanding of the literature, we were able to see what that means, and that could generate just a bunch of new potential paper. Like any of the paper is a research result, innovation, and then research is pretty similar. So I think that's interesting, and then fun application. Yeah, I just want to know how those your algorithm can will result in the shape of this say literature or academic industry.
Yeah, great point. Sorry.
Yeah, once you once you're done with this application, I really want to know.
Yeah, so actually that's a great point. So I think this actually did come up quite a few times amongst the team. It is actually, I've started scraping and gathering conference abstract and titles and paper titles and abstract. And the idea was to come up with like some sort of fun website where you click a button and it will give you a combinational idea of title and abstract. so it is definitely possible. And there are firms actually that are trying to do this, not with this method, but like humans are trying to do this. I would from the get-go say that lots of the output might be garbage, but there might be some good ones like doing this, and we'll work on it. I don't know how long will it take, but I actually did also talk to this postdoc at Harvard who was doing science of science, and we brainstormed a bunch of ideas. And one thing that's related to this, I'll share. This is something that you can do. You can take like a Web of Science and literature, scientific literature, right? And embed them using abstract. I mean, abstract has lots of information, right? Or you can maybe do with the introduction, some abridged version of the introduction if you want more information, and embed them in I don't know, idea space, right? And then you can now overlay citation network. And you can sort of, what you can do here is this within the idea space, the papers will be embedded and there will be a network of citation. And you can compare, contrast. There might be a cluster that are like far across, like spread across in the idea space. Right. And then there might be some clusters that are right next to each other, but there's no connection or citation, right? So you can do these kind of fun things. And we are trying to work on that too.
Yeah. Thank you.
Other questions?
How can AI assist HR departments with view to create future patents? With view to creating future patents. Mark, can you elaborate, please?
Yeah. Yes. How can like future HR departments want to employ new people? How can that help them assist? Because if you know a future patent is possible, how do you create the staff to create the patent?
I see. So the question is, how would an HR hire someone to become more innovative?
Yes. How would you?
Yeah. So I think that also came up. I was discussing this with the finance professor, and he was raising this similar point. Is how can you, but this was more about, I guess this was a more reverse, like how can you first identify patents that create more jobs, which is somewhat related, but I could imagine you could embed, you can co-train based on the say CV or someone's skill document and embed them within this same space of innovation space. You can sort of see how you can expand your maybe volume of your skills, of your firm's skill overall. I don't know how that might translate, like because
if you have a possible patent on the boundary of your space, how do you extend your knowledge boundary to capture that?
Right. I mean, what I'm saying is that you can embed the humans in the same space, and then try to cover that. However, that doesn't really guarantee that you as a firm, your firm could generate that. So I'm saying you could try to, what this algorithm can tell you is, here are some skills or technology that you can obtain by hiring a particular people. This algorithm can tell you this, but whether after hiring that person, they can now start producing this new patent is I haven't validated. I'm not sure how that could be, but it could tell you, oh, this candidate has a better fitted sort of skill set than another candidate. It can tell you these kind of things.
Right. So you could put together a team that could, object is to produce a certain patent.
Yeah, I guess you could try that.
Yeah.
I would go as far as saying it'll tell you the composition. You could come up with a team that has a particular set of composition of skills and knowledge, but whether they are able to work together to create this is a different matter. So.
Okay.
Great point.
Any other questions for Dr. Lee?
Oh, can I ask you a
Yeah.
question?
Go ahead.
Yeah, thanks to Kay for the great presentation. Learned a lot. So I think, so you're going to submit the paper very soon. So hopefully, maybe you will like share the innovation score so that other researchers can maybe rely on your research. That'll be very good.
Oh, you mean the scholarly thing that I haven't even started that?
No. For the patent, the firm
Oh,
innovation score. Yeah. So
Yeah,
that was
yeah.
very useful. Yes. Yeah.
yeah. Do that. Actually, yeah. That's a great idea. Because there are a lot of like tools, commercial tools that are trying to do using like word-based. It's not like these. That's a great idea. We'll look into that.
Yeah, recently, so MIS Quarterly, there was an editorial on the replication issue of IS research. So many of our, based on like large data set and computation, so people cannot really replicate that like you do. So maybe you can share the end products that later people can rely on your shoulder. So that'll be great. Thank you.
Thank you for the suggestion. Yeah, we intend to share the results, fruits in GitHub or something.
Good. Other questions? We have a few more minutes left. If there are any other questions.
Oh, I found someone wondering if VAE became a dominant family of generative models, or are GANs still being used as much or more? So there are a bunch of differences. So GANs are usually better at generating realistic looking things than VAE, which has more control. But you can now combine them and train VAEs adversarially, right? So you can add a discriminator and you can train it like a VA GANs. And there is a third step called wave, a flow-based model, which is, it takes long, it's a Gaussian process-based model where the realistic outputs are really realistic, but it takes a long time to train. And so there are a lot of different, there are like three set of families, and now they're getting sort of like combined. So VA is good for control. GAN's good for coming up with the realistic things. So people have combined them, GANs, and so you can do a lot of different fun things. There are so many different flavors of GANs and VAs now. Pops up every day. Great question. Thank you. Yeah, that's, I think, it.
Okay. Any other questions? Okay, doesn't look like. So again, I'd like to thank Dr. Lee for excellent presentation. I think was wonderful to see. Good discussion. Thanks for everyone to attend, and hopefully we'll see you at the next one. Thanks.
Thank you so much, everyone. Have a great one. Thanks for having me.
Bye.